Thank you ever so much for being here with me today. I think that there are some advantages and privileges of an old age, and one of them is that one is not so much constrained with the formal demands of methodology of science, and one may more freely wander in Platonic realm of forms and ideas. And what is more in Platonic form and ideas, like natural numbers. And this is why I decided to say something about natural numbers and ask the questions, are natural numbers natural? This is not a regular scientific paper, it's rather an essay, and it is our joint work with Jerzy Król, who is present here, and who is, I must say, my teacher as far as category theory is concerned. There is a very nice and quite an old paper by Paul Benacerraf under the title, What Numbers Could Not Be. It was published in 1965, and it started a long discussion about some philosophical aspects of real numbers. The paper, from philosophical point of view, the paper is rather technical, but it is written in a very nice literary style, and it has two protagonists, namely two young children or kids, Ernie and Johnny. And they are sons of two militant logicists. And they were taught mathematics not in the vulgar way, but strictly according logical demands. And to make a long story short, the number 3 for Ernie was this set. This is von Neumann's representation of the natural number 3. And for Johnny, number 3 was this set. They are different from that. This is a Merlo representation of a number. And the question which is starting the paper by Benacerraf is who was right, Johnny or Ernie? And the answer, after the long discussion in the paper at the end, this is the sort of answer given by Benacerraf. In giving the properties of numbers, you merely characterize an abstract structure. The elements of the structure have no properties other than those relating them to other elements of the same structure. And then Benacerraf formulates a number of postulates the number concept has to satisfy. A paper provoked a long discussion on mathematical structuralism. Some time after that, another paper has appeared, written by Colin McLarty. The title was Numbers Can Be Just What They Have To. And this is a sort of continuation or an answer to Benacerraf. And in this paper also there are two protagonists, this time two girls, Tasha and Brittany. And they were also subject to mathematical education, but now in a categorical style. After the years at the university, Tasha meets Ernie, and they confront their views. And it turns out that the categorical understanding of natural numbers meets all Benacerraf postulates, and even more. It goes even further. And this is what I want to comment and say something about. But the point is that in this talk, I leave aside the structuralist problem, and I want to see how category theory radicalizes our understanding of natural number and how it can change our understanding of the role of natural numbers in physics. And this is a sort of justification from my part. I am far from proposing a new approach to quantum gravity or some any fundamental theory, and in this way to contribute to the faith, fashion, fantasy style of doing physics. I don't want to do that. My only intention is to consider a possible conceptual environment that could broaden our horizon. And even if I mention in this talk some fundamental theories, it is only to give some food for our imagination. Well, so let us start with the concept of natural number as it is seen through the glasses of category theory. In category theory, there is something which is called the natural number object. And I want, well, to introduce the definition, or rather to explain what does it mean. Let's start from this diagram. And at the beginning, let us imagine that our category is just a set category. We are in the realm of sets. And then NC is a set of all natural numbers, infinite set of all natural numbers. And there are two arrows, arrow 0, arrow S. Arrow 0, when we are still in set theory, means the following. This number 1 denotes a singleton set composed of one element. Of course, the arrow from the singleton to another number picks up a certain number. And let us suppose that that is 0, which is picked up by this arrow. And then we have another arrow, S, which is successor function. Definition is here. If input is n natural number, then output is n plus 1. And now we go from set theory to some category NC, which is a certain category which satisfies some properties in order to have this definition meaningful, but I leave aside some technicalities. And now these are objects, and C is object in the category of C. And the counterpart of the singleton is the so-called terminal object of this category. And the terminal object is the object to which there is only one and only one arrow from any other object of this theory. And if we have this terminal object here, then the arrow picks up an element, not strictly an element, because in category theory objects have no elements in the sense of theory of sets. But the definition of an element is this arrow. If there is an arrow from the terminal object to an object, this means that this defines an element here. So elements are now arrows. And then we have a successor function as previously. And the natural number object definition is the following. The n and O, natural number object, is an object NC together with these two arrows from the terminal object to this object, where this is a successor function, such that for any other object y in this category and any arrows of that kind in this category, there exists exactly one morphism, this morphism from NC to y, making this diagram commutative. And this is what is called natural number object, and this is a natural numbers as seen in the category theory. And here are some explanations. The picture is the same, from the commutativity of this diagram, it follows this connection, this formula. So if we go this way and this way and replace the successor function with what it means, we get this formula. And this formula determines the operation of counting in this category. Here we have a successor function, so in series of counting of elements here, and with the help of this unique arrow, the counting is transferred here. So if we count something in this category, we must use this approach. The natural number object is unique up to isomorphism. And philosophically, it's interesting that NNO combines the aspect of an actual infinity, because this is an infinite object. It contains all natural numbers. If it is set theory, it is the set of all natural numbers. And also, it has something to do with potential infinity, because this morphism, this arrow, successor function, goes to potential infinity. Okay. And now a few words of justification. Why are we considering that? When doing macroscopic physics, of course, there is no reason to go outside the category of sets. Then objects of this category are sets, and arrows are mappings between sets. But works of Isham's group suggest that it is topos theory that is a correct environment for quantum mechanics. Toposes are special kinds of categories. And when we enter the area of quantum gravity, we should be open for all possibilities, in particular for a change from the set category to some other category which is better adapted to the game of concept played on this level. So such a possibility, at least from the philosophical point of view, should be taken into account. And if we decide to go from the set theory to some other categories in looking for more adequate concepts for, say, quantum gravity, then we should consider this diagram. This is category of manifolds, because physics happens on space-time. Space-time is manifold, so we must start with category of manifold. And then we have an arrow S. It is different arrow. It is not a successor function. It's something different, but the traditionally is also denoted by S. And then we have the category L. The category L is a so-called category of Lotzi. It's similar to the locus category, which is considered in algebraic topology. Then we can go with the help of the so-called Yoneda functor to another category, which is Preshev category. Well, I am. If I wanted to explain all these meanings and definitions here, it would take us too much time. The definitions are here, but I skip them. Well, and let's look now at the same diagram. The point is that the category of manifolds sits here in a full and faithful manner. So it is a well-embedded space-time in this. And also here, space-time, well, manifold category is fully and faithfully here inside that category. So let us imagine we are in the category of manifolds. And let's consider the real line, which is denoted by R. And we put this real line into the category of Lotzi. We obtain something like that. There are some continuous function on R, and L, it's only a symbol to tell us that it belongs to the category of Lotzi. And this is denoted by R, written in this way. And let's take a look at that symbol here. In L, in the category of Lotzi, in place of R, we have an old smooth function from R to R, such functions. And constant functions from here corresponds to real numbers from R. But there are much more functions than constant functions here. And all other functions are something new, which are produced by the very fact that the real line was embedded into a new category. And among these new numbers, there are also some infinitesimals, infinitely small numbers. For instance, nilpotent infinitesimals, which are defined like that. The number x is infinitesimal if its square is 0, although x is itself need not be 0. We see how the change of categories can modify mathematics. In fact, enrich mathematics. Unfortunately, the category of lots has some disadvantages from the interest of physics, so to speak. I will skip explaining in which these difficulties consist. So we should immerse this lotsy category into the Prešov category. The Prešov category is defined in this way that we consider some functors from opposite category to lotsy and to set with the values in sets. And also manifolds sit here in this Prešov category in a full and faithful manner. However, also this Prešov category has some unwanted properties. For instance, the R, this new real line, is not local ring. And again, we can improve the situation by changing Prešov category into a Schiff category. This is called Schiffification procedure. To do so, we introduce a Grothendieck topology on L, and this can be different in several ways. Especially two ways are especially interesting. One of them produces what is called Zariski topos, Z, and another one is what's called Basel topos, B. And in both these toposes, manifold sits faithfully and fully. So they are also good categories from the point of view of geometry. How natural number objects looks in the category of Prešovs? It is a constant Prešov given by this formula here. So let's notice that it looks very similar to natural numbers, but let's look here. They are not natural numbers as we are accustomed to them in the set environment, but they are functors from this category, which is opposite to lotsy category, to set. So numbers are now functors, different mathematical entity. And if we make a Schiffification, if we go from this Prešov theory to Zariski topos, then the Schiffification gives a constant Prešov like that, which is denoted in this way. But let's look at this footnote. In the case of Zariski topos, the Schiff associated with this constant Prešov, so it's a NNO in Zariski topos, is in fact described by equivalence classes of some n-valued locally constant bounded functions. So this is how natural numbers look in this category. But Zariski topos is so-called non-Archimedean topos because the following axiom is not satisfied. For every x belonging to real numbers, these new real numbers, there is a natural number n, such that this number x is smaller. Is smaller than n. So this natural axiom is not satisfied in Zariski topos, and also in Zariski topos the interval from 0 to 1 is not compact. So the geometrically is not a good category. But the situation change. Well, still will remain in the Zariski topos. It's interesting thing that in the Zariski topos there is also another object which is defined here, different than NNO, and it is called smooth natural number object, and it's different than that. And elements of this smooth natural number object are called S numbers, and we have this inclusion. So these smooth numbers include also non-standard elements, including also infinitely great numbers. So we see that mathematics is enriched here. And with these new smooth numbers, all before mentioned pathologies disappear. In particular, the interval from 0 to 1 is already compact. Internal logic of toposes is the intuitionistic logic, and the double negation law is not permitted. Consequently, if we look at this logical law, the double negation law, we cannot infer that X exists. Double negation should give now us assertion, but we cannot use the double negation law here. So we cannot infer that X exists, but only that it is not true that it does not exist, which is different. Therefore, in Zariski topos, there can exist non-empty objects, but we cannot claim that they have some elements. Such objects are called non-inhabited. This is the last obstacle to develop a differential geometry in Z. Such a geometry developed in Z is called synthetic differential geometry, SDG. And it can be, but this obstacle can be removed by improving the Grothendieck topology on L. And in this way, we change the Zariski topos into the Basel topos. But I said this is the last obstacle, these non-inhabited objects. But could it be also an advantage, perhaps? All strange things in mathematics usually have some good response in physics. We can think about, for instance, quantum void, which is something between nothing and something, like non-inhabited objects, something like that. It's, of course, very rough intuition. But let's go further, and let's go to Basel topos, in which there are no inhabited objects. The fact that in the topos theory the intuitionistic logic holds implies the weakening of logic, of course, because you cannot use the axiom of choice, you cannot use double negation law, you cannot exclude middle law. The fact that in some toposes, like in Zariski and Basel topos, NNO does not coincide with smooth NNO, leads to weakening of arithmetic. So in the sense that the arithmetic is weaker than standard Peano arithmetic, for instance, the strong form of mathematical induction does not hold. There is a series of papers and a stream of works which try to introduce category theory to physics, and the main protagonist of that stream is, I think, John Baez, and his most quoted paper is categorification paper. Categorification of set category, so changing from set to set category, is mainly the problem of aesthetics, although in science aesthetics also plays an important role. But on fundamental level of physics, changing to some other categories may turn to be necessary or at least interesting. Then we would have to change from natural numbers to some corresponding NNO or smooth NNO. Moreover, as we have seen when considering the Zariski topos, it might be necessary to replace NNO with some more natural smooth objects. It's interesting that in the Zariski topos, if you immerse in Zariski topos the manifold category, so manifolds see as natural numbers these smooth numbers and not standard NNO. One of the most fundamental and most mysterious problems in understanding physics is the origin of fundamental physical constants. And physical constants are real numbers. Well, should we also think about the categorification of physical constants in the sense of changing from standard real numbers to real numbers object? Because real numbers object is defined in an analogous way like natural number objects. Of course, we can also go and speak about also complex numbers as we wish. And this is the question. Suppose in the Zariski topos live some intelligent beings, and suppose they perform physical experiments in the Zariski world. What kind of numbers would the Zariskians obtain as output of their measurements? Probably smooth natural numbers and not usual ones. So philosophically, it's an extremely exciting field of possibilities. As Bias and Dolan remark, decategorification is an univocal concept. Some information is simply lost. To decategorize, we should simply use some functors which are forgetful functors. But categorification process, on the other hand, is not univocal. One is looking for an unknown information, and one can look for it in many different directions. And this could make things extremely interesting. Let's go to the beginning of this talk, when we mentioned Johnny and Ernie, Tasha and Brittany. And when Tasha and Ernie meet at the university, they agree that all Benes-Horraf's postulates regarding natural objects are fully satisfied by the categorical understanding of numbers. And then, when studying further category theory, they would probably reach the conclusion that what this theory, category theory, demands is even more radical than Benes-Horraf's postulates. We all remember the famous Kronecker saying, God make the integers and all the rest is the work of men. But we can add that if God created any numbers, we shouldn't expect they are so simplistic as those we invented ourselves. Thank you.